So last we did was the describing function of a relay with the dead zone. We had actually found out the describing function of a dead zone followed by a linear characteristics, but then we did the describing function of dead zone followed by a relay characteristics. Number 6, we'll conclude this today with two, three more describing functions. Dead zone with saturation, so dead zone with saturation so this is the nonlinear behavior that you will be seeing in this case. You have a dead zone followed by a linear behavior and then saturated output. Similarly, in the negative half region, dead zone, then linear behavior, and then saturated characteristics. Let this point be d by 2, let this point be s, similarly it will be minus d by 2 and minus s, and the slope of this curve, let it be equal to k. So we are applying a sinusoidal input. So corresponding to this, you will have an angle alpha. Corresponding to this, you will have an angle beta. So alpha will be equal to sine inverse of d by 2 divided by x, while beta will be equal to sine inverse of s divided by x. And the output characteristics, how will y omega t look like with respect to omega t? So y of omega t so there will be actually 3 cases. So for one case where x is actually less than d by 2, for magnitude of output, magnitude of the sinusoidal waveform less than d by 2, in that case what will happen is that your output will be simply 0, y omega t will be simply 0, since all of the output will be aligned with the dead zone part of the nonlinear element. And case 2, for x greater than d by 2 and x less than s, so this will be actually the output y omega t will be 0 for omega t greater than or equal to alpha, from 0 to alpha, and it will be equal to k times the input, k times the sinusoidal input, that is x sin omega t, for alpha to from alpha to pi, actually from alpha to pi minus alpha, there will be no beta in this case. And case 3, this case 2 is dead zone, that we have already done yesterday. Case 3 is that is actually what we need to focus on, where our x is greater than actually s, and also s is actually greater than d by 2. So in that case we need to find out the output waveform. So y of omega t will be equal to 0 for omega t varying from 0 to alpha. It will be equal to k s ks sin omega t for alpha to beta. From beta to from 0 to alpha, the output will be 0 because this will be falling under the dead zone period. From alpha to beta, the output will be matched with the linear curve, and that in this case is actually ks ks sin omega t, and then from beta to pi minus beta, it will be equal to the saturated output, that will be, say for example, it is m. I am assuming that this output is equal to m. Therefore, from beta to omega t to pi minus beta. Fine. So then pi minus beta to pi minus alpha, it will be again ks sin omega t, and pi minus alpha to pi, it will be equal to 0. Fine. So this is our omega t. So we can actually draw this curve. From 0 to alpha, it is 0. From alpha to pi minus alpha, it is sin omega t, and then it's saturated, and then again sinusoidal waveform, and then dead zone. So this is pi, then there will be beyond pi up to 2 pi again. So this here is alpha, this here is beta, this here is pi minus beta, this is pi minus alpha. So you can see from 0 to alpha, the output is 0. From alpha to beta, output is sinusoidal waveform. From beta to pi, it is saturated output, and it is saturated at value m. This m is actually nothing but this will be equal to ks. One correction here, k, this is k x sine omega t minus d by 2, like we did yesterday. Kx sine omega t minus d by 2. Similarly, k x sine omega t minus d by 2. This is m, and m is actually the magnitude of your saturated output, which is equal to k. In this case, it will be s minus d by 2, because our curve is starting from d by 2, not from 0. This linear curve. Fine. So this period multiplied by this period is actually x multiplied by the slope of the curve, that is k. That will give us this point, y is equal to mx, the straight line point. Fine. So this is our output, and if we complete this, this is again kx sine omega t minus d by 2 from pi minus beta to omega t to pi minus alpha, and again equal to 0 from pi minus alpha from omega t up to pi. So this is our curve that we have obtained. This is our sinusoidal waveform that is saturated, and that is actually a blank period from the start. So again, looking at this function, it is an OR function, and it has a half wave symmetry. So we can actually find b1 for this equal to 2 by pi 0 to pi y1 y omega t sine omega t using the Fourier transform, 2 by pi 0 to pi from 0 to alpha, it is equal to 0. So this will be 0 from alpha to beta y of omega t is equal to kx sine omega t minus d by 2, kx sine omega t minus d by 2 sine omega t d omega t plus beta to pi minus beta, it is equal to m, the magnitude, that is ks sine omega ks minus d by 2 sine omega t d omega t. Fine. And then you can have from pi minus beta to pi minus alpha, it is again kx sine omega t minus d by 2 sine omega t d omega t. Fine. Then from pi minus alpha to pi, it is 0, so this whole term will become 0. So you need to multiply these terms, then sine square omega t will be 1 minus cos omega t divided by 2, and substituting for alpha equal to sine inverse of d by 2 by x, and beta equal to sine inverse of s by x, you will get nx equal to k by pi 2 beta minus alpha minus sine 2 beta minus sine 2 alpha. This is your nx at an angle of 0 degrees. Fine. So this is your case of a dead zone followed by a linear behavior and then a saturated behavior. In this case, there will be 3 periods where the output will be 0, where the output will be constant, and where the output will be sinusoidal in nature. Number 6 that we'll be doing is number 7, backlash. So backlash we have seen let this point be b by 2, and therefore this will be minus b by 2. Let the width of this be b. Will be actually coinciding these 2 points. So what will be the output response for the system? You can see from 0 to pi by 2 the nonlinear system is varying linearly, but from some period, say for example this 0 to alpha, what is the case from 0 to alpha is that the nonlinear dynamics is negative. That means we will be still getting a sinusoidal waveform, but we'll be starting with from the negative region. And it will actually our output from 0 itself up to exactly this point, that is the width, that is actually pi by 2 on this input curve, from 0 to pi by 2. The output will be a sinusoidal waveform given by x sine omega t minus b by 2. Minus b by 2 will be subtracted from this. That will actually take care of the negative region of the nonlinear dynamics. Then from pi by 2 to beta, this point, actually instead of saying beta, we'll say this is pi minus beta. So that means beta was somewhere actually here in the negative region already. From pi by 2 to pi minus beta, now we'll be tracing back this path, and that means actually a linear flat path. That means our output will be saturated. What will be the output value? It will be simply equal to x minus b by 2, where x minus b by 2 is actually the magnitude of this backlash curve, x minus b by 2. So our output will be saturated in this region. From 0 to pi by 2, we have a sinusoidal waveform, and then our output is saturated. So this is pi by 2. This is actually alpha here, and then now we have a saturated output waveform from pi by 2 to pi minus beta. Then what happens is from pi minus beta up to, from all the way from here or here, this point will actually correspond to 3 pi by 2 on this curve. We again have a sinusoidal waveform, a linearly varying sinusoidal waveform from pi minus beta to 3 pi by 2. We'll be having a sinusoidal waveform given by x sine omega t plus b by 2. So we have a sinusoidal waveform like this. This will be up to 3 pi by 2, and from 3 pi by 2 to 2 pi minus beta, that will be somewhere around here. Our output will again be saturated, and then from 2 pi minus beta to 2 pi rather, we will again be having a sinusoidal output waveform. So this is 2 pi minus beta, this is our 2 pi curve. So from 2 pi minus beta, we'll be having from 3 pi by 2 to up to 2 pi minus beta minus x plus b by 2. This is a constant output, and it will be varying from 3 pi by 2 to 2 pi minus beta, and then let me write it here. It will be equal to again a sinusoidal waveform that will be given by x sine omega t minus b by 2 for 2 pi minus beta omega t up to 2 pi. Fine. So this is our curve that we have obtained. There is no symmetry in this case. It is neither an odd function nor an even. It's not an order range function. There is a quarter symmetry in this case. So what you have to find out both a1 as well as b1. In this case, a0 will be equal to 0. So you have to find out a1, that will be equal to 2 by pi 0 to pi y omega t cos omega t. So then you have to substitute those values from 0 to pi by 2 to pi by beta, pi minus beta to pi, 0 to pi by 2 to pi minus beta to 3 pi by 2 to we are only looking up to 0 to pi, so it will be 0 to pi by 2 to pi minus beta, and pi minus beta to pi. So that will be covering these first three x sin omega t minus b by 2, x minus b by 2, and x sin omega t plus b by 2 values. So you will substitute that, and then similarly b1 will be equal to 2 by pi 0 to pi y omega t sin omega t d omega t. So on substituting on finding out b1 again, a1 you will see it will be equal to x divided by pi by 2 plus beta plus 1 by 2 sine 2 beta, and this will be equal to minus x by pi cos square beta. Fine. Therefore n x for this case will be equal to under root of a1 plus b1 it will be equal to substituting these upper values a1 and b1 square divided by x, and the angle will be tan inverse of b1 by a1, and this will be valid for x greater than b by 2. If x is actually less than b by 2, the sinusoidal input, this will be valid for x greater than b by 2. For x less than b by 2, the describing function will be equal to 0. So this is about describing function of the backlash. You can do the describing function of also dead zone with relay and hysteresis. You can try that also. So that finishes our describing function of various nonlinear systems. Now in the next session we'll be seeing how describing function can be used for analyzing various nonlinear behaviors.